Welcome, everyone, to this explainer. Today, we're looking at a completely fascinating and, well, frankly, kind of alarming trend happening right now across global infrastructure, tech, and geopolitics. You see, we spend billions of dollars designing these absolutely perfect self-contained systems, but lately, we're seeing them fail. And not because the internal parts broke, but because supposedly external conditions have suddenly become the boss. They've become the governing variables. The boundaries of our systems are literally moving outward, and the environment has, quite literally, entered the architecture. Okay, let's dive right into this. As we go on this systems thinking journey today, I want you to keep one central question in the back of your mind. Just ask yourself, what quiet interface turns an apparently abundant resource into a usable capability? Because as you'll see, the resource itself, it's almost never the actual problem. It's the invisible bridge connecting it to our world that suddenly snaps. To show you exactly what I mean, just look at this completely absurd reality we're dealing with right now. Today, high-tech, multi-billion-dollar nuclear reactors in Europe are literally being brought to their knees by jellyfish and river mud. No, seriously. In France, massive jellyfish swarms are forcing reactors offline, and they're having to bring in fleets of vacuum trucks just to suck them out. Meanwhile, over in Hungary, river levels have dropped so incredibly low that they are actually sinking heavy barges into the Danube riverbed. Why? Just to push the water level up high enough to keep their nuclear plant running. So, how does this even happen? Well, it all comes down to our mental models, right? Our traditional diagram of nuclear power usually looks like this neat, simple little box. You put the uranium in, the reactor does its incredibly complex magic, and boom, electricity comes out. It's neat, it's isolated, and it treats the outside environment as just a passive backdrop to the engineering. But this brilliantly illustrates our core problem today. The real system absolutely does not stop at the concrete walls of the power plant. The true operational system is way bigger. The reactor depends on a water source, which relies on river flow and river temperature. And they're governed by strict environmental limits on how much heated water you can safely pump back into the ecosystem without, boiling the fish. Climate adaptation isn't just sitting next to energy policy anymore. It is baked right in. It's a fundamental structural part of the energy architecture. The river is literally part of the reactor. What we're witnessing here is a classic systems engineering concept called constraint migration. We spent decades building up enough nuclear generation capacity thinking, great, we solved the bottleneck of power creation. But actually, solving that bottleneck simply moved the constraint somewhere else, specifically into cooling water availability. Constraints rarely just vanish into thin air, right? They just change clothes. Moving on to part 1, constraints and correlated fallback failures. Let's see how this plays out. Let's step outside of energy for a second and look at global supply chains. Take the situation with Ukraine's green exports. When the war blocked their primary shipping routes through the Black Sea, they pivoted to what seemed like a super logical backup plan, shipping through their largest port on the Danube River. But right as they became entirely dependent on this alternate route, the whole region got hit with historic droughts, causing record-low river levels. And then, to make matters worse, the port infrastructure itself was targeted. This right here is a textbook example of a correlated fallback failure. In systems design, it's super easy to just draw a second arrow on a whiteboard and say, boom, resilience. But a backup path is only valuable if its failure modes are actually different from your primary path. If your primary route and your backup route get wiped out by the exact same geopolitical conflict, or if your backup relies on a river that completely dries up, well, they share a failure domain. A second line on a map isn't automatically resilience. Okay, let's jump into part 2, declared versus operational reality. This brings us to a fascinating way systems break down, when the people managing the system fundamentally disagree on what state the system is actually in. Look at the Strait of Hormuz. Roughly a fifth of global oil shipments pass through there. Right now, we have this massive clash of declared states. The U.S. government declares the waterway is under their protection and navigation is safe. Meanwhile, Iranian officials declare the exact opposite, that the strait is under their management and requires Tehran's permission to transit. But listen, if you are a global ship owner, all of this political posturing is practically useless to you. Your operational state relies on a much harsher, practical question. Can I actually ensure my cargo, keep my crew alive, and arrive safely? The operational reality on the ground often violently disagrees with the declared states of governments. Let's move to a different scenario and see how this builds. Following the tragic earthquake in Colombia, we saw this exact concept of operational reality play out. A hospital building might be completely destroyed, the physical box has failed, but if medical staff are successfully treating patients in tents right outside, the actual healthcare capability has survived. On the flip side, an intact hospital building is completely useless if broken roads prevent ambulances from ever reaching it. True resilience means preserving the capability itself, not necessarily the box that used to contain it. All right, part 3, the cyber authority surface. Let's shift into the digital world. In geopolitics and cyber, the expanding boundary isn't a river or a road, it's legal. There's a new U.S. national security memo that creates a program allowing vetted private companies to conduct offensive cyber operations against foreign criminal organizations under federal direction. To really grasp the gravity of this, we need to introduce a new term, the authority surface. This is the complete set of interfaces through which permission to observe, modify, or disrupt a system can be exercised. By handing offensive cyber authority outside of strictly government networks, that authority surface is massively expanded. We have to look past the politics for a second and look at the actual system architecture. I mean, who confirms a server actually belongs to a criminal group? What happens if innocent companies are sharing that exact same cloud infrastructure? What if disrupting it accidentally destroys evidence another government agency was watching? When authority crosses from just observe to act in the hands of a private company, the coordination and escalation risks are just immense. The system boundary has moved outward, and the complexities literally multiply overnight. Okay, part 4, AI economics and reality checks. Now, what's really interesting about this slide is what it reveals about the real bottleneck in AI. We hear so much hype, but let's look at the fragile physical dependencies holding it all together. You can have billions of dollars in cutting-edge GPUs, vast amounts of land, and massive cloud contracts, but your state-of-the-art data center might just sit there completely dark and useless. Why? Because it's waiting on a traditional medium-voltage electrical transformer, and those currently have a 4-year manufacturing lead time. It's crazy. The AI revolution is bottlenecked by physical equipment with design lineages that predate the internet. And because of these massive operational realities, enterprise AI strategy is totally shifting. It's no longer just a race for maximum intelligence. Organizations are realizing that for most of their daily tasks, the absolute cutting-edge frontier capability is way more than they actually need. So the procurement question is pivoting. It's moving away from which model is the absolute smartest to which model clears our reliability threshold at the lowest total operational cost. We're really seeing the rise of best enough, open-weight models that prioritize right-sized economics over sheer computational brute force. We also need to apply a serious reality check to AI threat models. Recently, Taiwan experienced cyber campaigns targeting their government systems. Now, it is very easy to spin up this cinematic narrative about autonomous AI supervillains, independently deciding to hack a country. But we have to look impartially at the evidence we actually have. The practical, supported reality is that attackers used a hybrid approach, humans assisted by AI agents for faster reconnaissance and credential harvesting. The real threat isn't some autonomous AI army. It's that a mediocre human attacker plus good AI simply becomes a much faster mediocre attacker. We have to design our defenses around the practical threat, not the sci-fi one. And this is exactly why the new NIST TEV AFLON framework is so crucial. It finally gives us the framework to just refuse bogus, oversimplified certainty. We can no longer accept blanket statements like, Model X scored a 92 on a benchmark, therefore it is totally safe. Safe for what exactly? Under what assumptions? The NIST framework treats AI verification as highly context-dependent. It forces us to ask, what does this benchmark actually give you permission to conclude about the system's operational reality? Let's wrap this up with part 5, the quiet interface. So the crucial point I want to leave you with is perfectly captured by what's happening at that Gravelines nuclear plant in France. To keep one of Europe's largest, most sophisticated energy facilities from literally melting down, they rely on a control loop that goes like this. Stationary cameras spot the jellyfish, which then triggers local fishermen to mobilize their boats, trawl the swarms, and deploy those vacuum trucks to clear the intake canals. The ultimate safety mechanism for a marvel of modern physics is a group of local fishermen. And this proves our whole argument today. The scarce thing is almost never the resource everyone is arguing about. It's not the uranium, it's not the AI capital, it's not the cyber expertise. The true scarcity, the true point of failure, is the quiet interface that converts that raw resource into a usable capability. It's the cooling water, the electrical transformer, the local fisherman. These interfaces are thoroughly unglamorous, which is exactly why they are routinely left off the architecture diagrams, and it's exactly why they deserve our utmost attention. I want to leave you with a thought to apply to your own work, your own systems, your own world. As you look at the complex systems you rely on every single day, just ask yourself, what apparently abundant resource becomes completely useless when one quiet interface stops working? Thanks so much for joining me for this explainer, and I'll see you next time.